the atom from chemistry, like its structure and what isotopes are. We'll also look at how electrons can move between different energy levels. In the center of every atom is a nucleus, which contains individual protons and neutrons. The protons are positively charged, so 1+, while the neutrons are neutral. And we say that both of them have a relative mass of 1. Then, orbiting around the nucleus, in shells, we have electrons, which are about 2,000 times smaller than protons or neutrons, and have a negative charge of 1-. If you look at a periodic table, each box is known as a nucleus symbol, and represents a particular element, like this one for lithium. Inside the box is all the important information that you need to know about that element. On the right, we have the elemental symbol, which represents the element, so Li for lithium. In the bottom left, we have the atomic number, which is how many protons the atoms of that element have. And this one's really important, because it's the number of protons that determines which element it is. So if our atom over here had 4 protons instead of 3, then it wouldn't be lithium anymore. In the top left, we have the mass number, which tells us the total number of protons and neutrons together. So lithium's is 7, because it has 3 protons and 4 neutrons, which together make 7. Now, the nucleus symbol doesn't directly tell you the number of electrons. You just have to remember that the number of protons and electrons in an atom is the same, which is why lithium has 3 electrons. The next thing we need to look at are isotopes. The isotopes of an element are atoms with the same number of protons, so the same atomic number, but different numbers of neutrons, so different mass numbers. For example, as well as lithium-7, which we've been looking at so far, we can also get lithium-6, which has 3 neutrons, and lithium-8, which has 5. So these 3 would all be classed as isotopes of lithium, because they all have the same number of protons, but different numbers of neutrons. Now, generally, only 1 or 2 of an element's isotopes are actually stable. The other isotopes, which are unstable, tend to decay into other elements by emitting radiation, like alpha, beta, or gamma radiation. Or sometimes they just emit neutrons. We call this process radioactive decay, and we'll take a closer look at it in the next video. For now though, we need to take a closer look at the electrons. The electrons in an atom are arranged in a series of energy levels, which we call shells, with each shell getting progressively further away from the nucleus, and increasing in energy level. Although electrons normally stick to a single shell as they orbit the nucleus, they can occasionally jump up to a higher energy level if they gain enough energy. And at that point, we'd say that the electron has become excited. The energy for this comes from electromagnetic radiation, and it will only work if the radiation carries just the right amount of energy to get the electron from one energy level to the next. Pretty soon afterwards though, the electron will fall back down to the lower energy level, and will re-emit the energy as electromagnetic radiation. The very last thing we need to look at is ionization. Very occasionally, one of the outermost electrons could absorb so much energy that it's able to completely leave the atom. This leaves the atom with more protons than electrons, and so it's left with a positive charge, which means that we now call it a positive ion, rather than an atom. Also, if you hear the term ionizing radiation, all it means is that it's able to knock electrons off atoms, and so ionize them, like we just did for lithium. ionic bonds. And to explain this, we'll take a look at some dot and cross diagrams. First though, I just want to recap what ions are. We said in a previous video that ions are formed when atoms lose or gain electrons. And we can show this happening with equations. For example, a sodium atom will go to form a sodium 1 plus ion plus 1 electron. We know this because if we look at a diagram of a sodium atom, it has 1 electron in its outermost shell that it needs to lose in order to become stable. Because remember, stability is all about having a full outer shell. Meanwhile, for chlorine, we'd write that chlorine plus an electron, which we can see it needs to complete its outer shell, goes to form a 1 minus chloride ion. Now, this is all well and good in theory, but in real life, these reactions don't happen in isolation. Instead, we normally talk about a transfer of electrons, from an atom that has too many, like sodium, to an atom that doesn't have enough, like chlorine. Once this electron has been transferred, both atoms become ions, with full outer shells of electrons. So we put big square brackets around them, and their charge in the top right corner. The important bit here is that the two ions have opposite charges, so they'll be attracted to each other by electrostatic forces to form an ionic compound. We call this force an ionic bond, and it's really strong, similar in strength to covalent bonds, which we cover in another video. The way that we've drawn our compound here is known as a dot and cross diagram, and you'll often be asked to draw things this way in your exam. To do it properly, there are a couple of features to notice though. One is that we've drawn the electrons of one atom as dots, and the other as crosses. This is so that we can tell which electrons belong to which atom. And you should show the movement of any electrons with an arrow. Notice that in this dot and cross diagram, we've shown every electron shell of the atoms. Sometimes though, you'll be told you only have to draw the outermost shell, which is a bit quicker to draw. And for our example, it would look like this. Let's consider a harder example. Draw the dot and cross diagram for the formation of magnesium chloride, MgCl2. Only draw the outermost shells. Now this time, we can see that we have 3 atoms in the compound, rather than 2. To start, let's draw out our reactants. We have magnesium, which has 2 electrons in its outer shell that it wants to get rid of, and we have 2 chlorines, both of which have 7 outer electrons, so we need 1 more each. The next step is to think about where the electrons could move to make all the electrons happy with a full outer shell. And as a general rule, electrons will move from the metal to the non-metal. So in this case, magnesium can give 1 electron to each of the 2 chlorines. As a result, we'll end up with a magnesium 2 plus ion and 2 chloride 1 minus ions. This is now pretty much done. However, in dot and cross diagrams involving more than 2 ions, we generally arrange the ions like they would be arranged in a real compound. So because the chlorides would both be attracted to the positive magnesium, we place them on either side of it. Form covalent bonds by sharing electrons. And we'll also see all the different ways that we can draw these covalent bonds. To very quickly recap, we've already seen how some atoms can form ionic bonds by transferring electrons from one atom to the other. This makes oppositely charged ions that are then attracted to each other through electrostatic forces, which hold them together. And the reason that they transfer these electrons is so they both get a full outer shell. Now, this works great when one of the atoms has too many electrons and the other one has too few, like with sodium and chlorine. But what about when we have 2 non-metal elements, like 2 chlorine atoms? Well, in this case, both of them need an extra electron to get a full outer shell, so giving electrons to each other isn't going to help. Instead, what they can do is share some electrons, and as each atom needs 1 extra electron, they each share 1 of their own, so that together 2 are being shared, and they each get 1 extra. The way that we've drawn this is called a dot and cross diagram. And when you do these, you need to make sure that you draw one of the atoms with dots and the other with crosses, so that we can tell which electrons belong to each. Also, even though we've only drawn the outermost shell of each atom here, you might sometimes have to draw all of the shells. Just make sure you check the question to see what they want. An easier way to draw covalent molecules, though, is with a displayed formula, where we just write the chemical symbols of the atoms and use lines to join the atoms that are covalently bonded together. The great thing about these is that it's easy to draw big molecules that would take too long or be too complicated to draw as dot and cross diagrams. For example, this here is a molecule of sugar called glucose, which you don't need to know about specifically, but you do need to be able to recognize that this is a displayed formula. The downside of displayed formulas, though, is that they don't show you anything about the 3D shape of the molecule. For this, we can use a 3D model, which tries to show how the atoms are actually arranged in real life. For a slightly harder example, let's try to draw the covalent bonding in ammonia, which we just saw. It has the molecular formula NH3, so we can tell that there's 1 nitrogen and 3 hydrogen atoms, and the first step is to draw all of these out. In our example, we'll only draw the outermost shells. The next step is to think about how these atoms can fit together so that all of them have full outer shells. Remember that because this is hydrogen's first energy level, it can only hold a maximum of 2 electrons, so each hydrogen is going to need 1 extra electron to fill their shell. Whereas because this is nitrogen's second energy level, it can hold a maximum of 8 electrons, so it's looking for an extra 3 electrons to become full. So if each hydrogen shared 1 electron with the nitrogen, then all of the atoms would have full outer shells. And that would be our dot and cross diagram all done. Or if we wanted the displayed formula instead, we would just rub out all of the shells and electrons, and instead place lines wherever electrons were being shared, which just means placing a line wherever there was a covalent bond. Now, when it comes to the 3D model, things get a bit trickier, because it's hard to predict what shape the molecule will make. Luckily though, you don't have to know this just yet, you just need to be able to recognize them. The last thing we need to cover is the types of substances that covalent bonds can make. The examples we've seen so far, like chlorine and ammonia, are called simple molecular substances, which are small molecules in which the atoms in the molecule are joined by strong covalent bonds. But between the individual molecules, there are only weak intermolecular forces, which are easily broken. Other simple molecular substances worth knowing are water, which is H2O, and methane, which is CH4. Covalent bonds can also be used to make much larger structures though, such as polymers and giant covalent structures. We cover both of these in other videos, but basically polymers are long chains made up of lots of repeating units, which we call monomers, and are used to make things like plastic bags and t-shirts. Meanwhile, giant covalent structures are things like silicon dioxide, diamond, and graphite, which can involve billions or trillions of atoms arranged in a regular lattice. And because all of the atoms are joined by covalent bonds, they're really strong. By covalent bonds, in which they share electrons so that all of the atoms have full outer shells. Sometimes this results in small molecules, such as chlorine or ammonia, and we call these simple molecular substances. In other cases though, nonmetals bond covalently to form giant covalent structures, like diamond, graphite, or silicon dioxide. And in today's video, we're going to look at the respective properties of each of these, and then finish up by taking a closer look at the structure of silicon dioxide. Now, the first thing to know is that covalent bonds are really strong, which means that a lot of energy is going to be needed to break apart any atoms that are covalently bonded to each other. So if we consider a simple molecular substance like chlorine, the atoms within each molecule will be strongly bonded together. However, in order to melt or boil chlorine, we actually don't break these strong covalent bonds. Instead, we only need to break the weak forces that exist between different molecules, which we call intermolecular forces. Because of this, we only need very low temperatures to melt or boil simple molecular substances. For example, chlorine boils at -34 degrees Celsius. Although these intermolecular forces are individually quite weak, the more of them that a molecule has, the stronger the overall attraction is going to be. For example, let's compare the halogens, chlorine, bromine, and iodine. Because we're going down the group, the atoms and thus molecules are getting bigger, so there'll be more intermolecular forces between them. This in turn means that more energy will be required to break them all, so the melting and boiling points should increase as you go down the group, which they do, as bromine has a boiling point of 59 degrees, and iodine doesn't boil until 184 degrees. There's no need to remember these specific numbers. You just need to understand that the boiling point increases as you go down the group because the molecules get larger, so there are more intermolecular forces between them. Another property to note is that simple molecular substances don't conduct electricity, because there are no free electrons, and the molecules themselves have no electric charge. You'll see this point again and again in chemistry. In order to conduct electricity or heat, substances have to have some electrons or ions that are free to move about. So moving on to giant covalent structures, these are made of huge numbers of non-metal atoms that are all bonded to each other by covalent bonds. And they're generally arranged into regular repeating lattices, which just means that their structure kind of repeats over and over. The three important examples are diamond, graphite, and silicon dioxide. The main things to remember about these structures is that they're very strong and they have high melting and boiling points, because we'd have to break all of these strong covalent bonds in order to melt them. The other property to know is that they generally don't conduct electricity, because they don't contain any charged particles, even when they're molten. An exception to this though is graphite, which we take a closer look at in another video along with diamond, which are both made of carbon atoms. Silicon dioxide, on the other hand, is made of silicon and oxygen atoms in a ratio of 1 to 2. It's also known as silica, and is the main component of sand. You won't have to draw it, but you do need to be able to recognize giant covalent structures like this. Now, the key thing to take away from this video is that simple molecular substances are small molecules that are made up of just a few covalently bonded atoms, and the separate molecules are only joined together by weak intermolecular forces. Meanwhile, in giant covalent structures, all of the atoms are covalently bonded in regular repeating lattices, which makes them much stronger and gives them much greater melting and boiling points. Of two allotropes of carbon, diamond and graphite, and we'll consider the other allotropes, graphene and fullerenes, in the next video. First though, you might be wondering what an allotrope is. Basically, allotropes are different structural forms of the same element in the same physical state. So if we consider carbon in the solid state, it can take lots of different forms, like diamond, graphite, or fullerenes. So these are all different allotropes of carbon. Both diamond and graphite are giant covalent structures, which means that they're made of a regular lattice of covalently bonded atoms, which makes them both very strong. In diamond, each of the carbon atoms is covalently bonded to 4 other carbon atoms, which is the maximum number of bonds that carbon can make. This forms a regular 3D pattern, which you're fortunately not going to have to draw, but you do need to be able to recognize this sort of structure. As each of these covalent bonds is really strong, it will take loads of energy to break them, and so diamond itself is very strong and has a really high melting point. However, it doesn't conduct electricity because it has no free electrons or ions that can move around. Now let's compare these features of diamond to those of graphite. First, each carbon in graphite is bonded to only 3 other carbon atoms, rather than 4 in the case of diamond. Second, the atoms are arranged into hexagons that together form large flat sheets, which are then arranged on top of one another to form lots of layers. However, these individual layers are only held together weakly, as there are no covalent bonds between them. This means that they're free to slide over one another, which makes graphite relatively soft when compared to diamond. That said, graphite still has a very high melting point, because the individual layers are strongly held together with covalent bonds. Now, do you remember how earlier we said that carbon atoms can make 4 covalent bonds each, but in graphite they only make 3? Well, that means that each carbon atom in graphite has 1 spare electron that it's not using in bonding. Instead, this electron becomes delocalized, which basically means that it's free to move around. And all of these free electrons allow the graphite to conduct electricity and heat. Before we finish, it's worth mentioning that a single layer of graphite is known as graphene, and scientists can actually isolate these individual layers and use them to make other structures, such as spheres and tubes. We call these structures fullerenes, and we explore how they work in the next video. But we'll spend most of the video looking at the many uses that they have. As we said in our previous video, allotropes are just different structural forms of the same element in the same physical state. So in this case, different forms of solid carbon. In that video, we looked at the allotropes diamond and graphite, and saw that graphite is made up of lots of layers. Each of these layers is known as graphene, and their structure of multiple repeating hexagons, with each carbon being bonded to 3 other carbons, makes them really strong. And because each of the atoms donates 1 of its electrons to a delocalized pool of electrons, graphene can also conduct electricity, which makes it useful in making electronics. Now, graphene is completely natural, and we can get it from the ground in the form of graphite. But what scientists have started to do is take these strong but tiny sheets and make stuff out of them, like tubes. They've also made similar sheets, but with pentagons or heptagons, which make the sheets curve into spheres. And these tiny tubes and spheres, which we call fullerenes, can be used for all sorts of things. For example, scientists are able to form the spheres around other molecules, such as drugs, so that it acts like a cage, and can be used to deliver the drugs to certain areas of the body. Or because fullerenes have a large surface area to volume ratio, as all tiny things do, they could be used to make industrial catalysts, which are used to speed up the rate of chemical reactions. Meanwhile, the tubes, which are known as nanotubes because they're so tiny, can be used in nanotechnology, and in electronics because of their ability to conduct electricity. They can also be used to strengthen other materials, like tennis racket frames. This is because of their very high length to diameter ratio, which is just a technical way of saying that they're very long and thin, which allows them to add strength to the material without adding very much weight. The very first fullerene made, though, was one of these spheres, called the Buckminster fullerene, which is a hollow sphere made of 60 carbon atoms, so it has the formula C60. We call technology that uses these sorts of tiny structures nanotechnology, and it's now being used in loads of industries, from medicine and batteries to food and fashion. The main point to take away, though, is that fullerenes are allotropes of carbon with hollow shapes like spheres or tubes, and we use them for all sorts of things. Like bonding, which is the type of bonding you get between metal atoms, and we'll see how this gives rise to the characteristic properties of metals. Then lastly, we'll consider how alloys differ from pure metals. To recap, we've already seen that metals bond to nonmetals through ionic bonding, and that nonmetals bond to other nonmetals through covalent bonding. Now we turn to how metals bond to other metals, which we call metallic bonding. If we think of a solid metal, it basically consists of a giant structure of atoms that are arranged in a regular pattern. In this picture, we've shown each atom surrounded by the electrons in its outermost shell. When all these atoms are together in a metal though, they actually give up these outer shell electrons and share them with all the other atoms in the metal. This means that the atoms will all become positive ions because they've lost negative electrons. And because those electrons are now free to move about, we call them delocalized electrons. So there will now be loads of strong electrostatic attraction between the positive ions and the negative electrons. And it's these forces of attraction which hold everything together in a regular structure. So we call this metallic bonding. This gives the overall metal strength, and means that most metallic structures have high melting and boiling points, so are solid at room temperature. They are also good conductors of electricity and heat, because the delocalized electrons can carry electrical current and thermal energy throughout the structure. Another important property is that metals are malleable, which means that they can easily be bent or hammered into shapes, for example into thin sheets. This can be a bit confusing because we think of metals as being strong, and in many ways they are. But the fact that metals have such a regular structure means that the different layers can slide over one another. So they're not quite as fixed as you might have thought. At least that's the case for pure metals. If we want a harder metal that won't bend so easily, then we can make alloys, which contain two or more different elements. We make these either by mixing together two different metals, or sometimes a metal and a non-metal. And we generally pick elements that have different sized atoms. The reason that this helps is that the combination of different sized atoms disrupts the metal's regular structure, and means that the layers can no longer slide over one another, making the alloy much harder than pure metal. In our example here, we've shown steel, which is made up mostly of iron, but also contains 1 to 2% carbon. It also sometimes contains chromium, manganese, or vanadium, depending on which properties we want it to have. And this gives it the strength that it needs to be used in things like cars and planes.